Hello, in this video I'm going to solve the following problem for you. So let us read the problem. Evaluate the following integral. Integral of square root of 1 minus x squared over x cubed dx. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, one possible answer that you will get is as follows. 1 over 2 ln of 1 plus square root of 1 minus x squared minus a half ln of absolute value of x minus square root of 1 minus x squared over 2x squared plus a constant c. Okay, now let us solve the problem. So we want to calculate this indefinite integral. And of course, this is a very famous combination when it comes to the topic of calculating integrals. So if you have studied the lesson, hopefully you realize that you have to use one good way, of course, is to use the trigonometric substitution. So the substitution that I will use is to introduce a new variable theta as sine inverse of x. Okay? So what is the consequence of this? If theta is sine inverse of x, of course, by the definition of sine inverse, sine of theta becomes x. Moreover, if theta is equal to sine inverse of x, it means theta belongs to the range of the sine inverse function, which we know this is the closed interval from minus pi over 2 to pi over 2. And it will be important later on, you will see this. So this means that theta is somewhere from minus pi over 2 to pi over 2. So in principle, it means either theta is in the fourth quadrant or in the first quadrant of trigonometric circle. Okay, but when I introduce a variable, I have to rewrite my integral in terms of only this new variable theta. Okay, so to do this, I need dx. Okay, that's simple, because x is equal to sine theta. This means that dx is the derivative of sine theta, which is cosine theta, multiplied by d theta. Okay, and I have to rewrite everything in terms of theta, yes? So square root of 1 minus x squared becomes square root of 1 minus, instead of x I put sine theta, so it becomes sine theta squared. But this is very famous. It becomes square root of cosine theta squared. 1 minus sine theta squared is cosine theta squared, and we know that this becomes absolute value of cosine theta in general. But exactly because of this part, I know that theta is in the first or in the fourth quadrant, and in both cases cosine theta is non-negative, and I don't need the absolute value sign, so I can remove the absolute value sign. Okay, so if I call this integral I, then I can rewrite my integral in terms of the new variable theta as x to the power of 3 means sine theta cubed. Instead of dx here, I put cosine theta d theta. And instead of this expression, I simply put cosine theta. Okay? And then, of course, this becomes cosine theta squared divided by sine theta cubed. But I can write it as sine theta squared, but there is one sine theta left in the denominator, and I write it in this form. Okay, and then of course this is nothing except cotangent theta squared, so this becomes integral of cotangent theta squared, and then this becomes cosecant theta d theta. And now I have to calculate this integral. Okay, so how can I calculate this integral? I want to use the method of integration by parts to calculate this integral. Why the method of integration by parts is useful? Because you can view it in this way. Instead of cotangent theta squared, I can write as cotangent theta, and then another cotangent theta, cosecant theta, so I can write it as cosecant theta, and then cotangent theta. So cotangent, cotangent becomes cotangent squared, and then I have d theta. And this is the standard form of an integral for which method of integration by parts is useful. So you know, when you have an integral of this form, integral, oh, if I have an integral of this form, so that I have a function f of x, and then I have the derivative of another function, g prime of x dx, this type of integral should look familiar to your eyes. Whenever you see this pattern that in which you have a function and multiply it by the derivative of another function, then the method of integration by parts might be very useful by taking this part to be u and this part to be dv. Okay? So the integral of u dv then can be written as uv minus integral of v du. That's the formula of integration by parts. But whenever you detect this pattern in which that you have the integrand as a product of two functions, a function and the derivative of another function, you need to remind yourself about the possibility that I can solve this integral using integration by parts. Okay, so I call this integral I, so let me call this integral I, and I want to calculate this. And this pattern emerges because I have a function which plays the role of the f function, and then hopefully you know that this is the derivative of cosecant function. So this part is the derivative of another function, and you see that the same pattern emerges here. So that would be very helpful if I take this one to be u and this one to be dv. And then on the right hand side, I need to have u and v. I also need to have du. Okay, so this means that I take u to be cotangent of theta, but because I need du on the right hand side, I take the derivative. The derivative of cotangent is minus cosecant theta squared d theta. Then I take this one to be dv, as I mentioned. So cosecant theta, cotangent theta, d theta. Then if I ask you what v is a function whose derivative is this one. The derivative of cosecant theta becomes minus cosecant theta, cotangent theta. So v becomes minus cosecant theta. And then if I plug these back into the formula of integration by parts, I have I is equal to u times v. This is the u and this is the v. So it becomes minus cosecant theta, cotangent theta, minus the integral of v times du. V has a negative sign, du has a negative sign. When I multiply them, it becomes positive. Then this becomes cosecant theta to the third power. Yes. Okay. So this is the integral. I don't know. In principle, this is a standard integral, but the trick to calculate this is to use the integration by parts two times. Use the integration by parts as solving an equation for I. But here, might be we can do better. Okay, so what I can do, I can write it as minus cosecant theta, cotangent theta, and then minus. This cosecant theta to the power of 3 can be viewed as cosecant theta multiplied by cosecant theta squared. But this one can be written as 1 plus cotangent theta squared. This is the standard formula, yes? And then if I multiply this here, it becomes cosecant theta plus cosecant theta cotangent theta squared. So this integral can be broken into two integrals. One's the integral of that, and then an integral of this. But be careful, this minus sign is the overall minus sign, so it will affect this one and this one. So then it becomes minus integral of cosecant theta d theta minus the integral of cotangent theta squared. I'm intentionally writing this first, and then cosecant theta d theta. Why I did that, so if you don't mind, let me bring I down. But what is interesting is that if I ask you what is the name of this integral, you immediately realize that this is the same original integral. Yes, I call this integral I, so this is again I. But the good news is that I have a negative sign here, so even though this is I, this is minus I. Then I move I to the other side. I have an I here, that one moves there, it becomes 2I, is equal to minus cosecant theta cotangent theta. And this is also a famous integral, so I just write the formula. So it becomes minus, which is plus, ln of absolute value of cosecant theta plus cotangent theta. And then, of course, I have a constant, but let me add the constant at the very end after dividing everything by 2. So I becomes 1/2 cosecant theta cotangent theta plus 1/2 ln of absolute value of cosecant theta plus cotangent theta plus a constant at the end. So in principle, I am done. I was able to calculate my integral I. The only thing is that I have expressed it in terms of my new variable, but I have to switch back to my old variable, which is x. So I have to be able to rewrite everything in terms of theta now in terms of x. And I think that's also a standard trick. So what I have to do, I have to calculate cosecant theta, which is very simple. So cosecant theta is by definition 1 over sine theta. But what is sine theta is nothing except x. So this is just simply 1 over x. But if I ask you what cotangent theta is, we have this formula that 1 plus cotangent theta squared is cosecant theta squared. I just used it there. Okay, what is cosecant theta? It is 1 over x, so this is 1 over x squared. So it becomes 1 plus cotangent theta squared is 1 over x squared. But I am looking for cotangent theta squared, so I move 1 to the other side. Yes, it becomes 1 over x squared minus 1. If I take the common denominator, so this becomes this. Oh, sorry, there's no square root yet. It becomes 1 minus x squared. Okay, but then if I want to find the cotangent theta, so cotangent theta becomes the absolute value of cotangent theta becomes what? It becomes square root of 1 minus x squared over x. Yes, so over actually absolute value of x. So this means that cotangent theta is actually plus or minus square root of 1 minus x squared over x. Okay, but we need to understand which sign is actually the correct sign. Okay, might be that is not a good idea. Let me stop here and let us stop here and then discuss about the signs. Okay, so let us see what happens here. So you know that this means that x should be somewhere between minus 1 and 1. Otherwise, this square root is not defined at all. Okay, but then I can consider it in two cases. Either x is between 0 and 1, or it is between minus 1 or 0. Okay, so I have these two scenarios. But let us say that x is between 0 and 1. If x is between 0 and 1, I do not need this absolute value sign because x is non-negative. And then, and of course here, x cannot also be 0 because then I will have problems with the denominator. So let me take that 0 out. Okay? Okay, but if x is between 0 and 1, I do not need the absolute value on the right-hand side. But I will not need the absolute value sign on the left-hand side. Why? Because if x is between 0 and 1, because sine inverse of x is theta, then it means that theta is in the first quadrant. And if it is in the first quadrant, cotangent theta is also positive, so I don't need absolute value sign there either. So this means that for this case, I can safely write cotangent theta is equal to square root of 1 minus x squared over x. But this is for the case that x is between 0 and 1. But now, if x is between minus 1 and 0, what will happen? The right-hand side becomes a square root of 1 minus x squared over minus x. Because if x is negative, if I want to remove the absolute value sign, I have to compensate for that change by putting a minus sign here. But now look, if x is between minus 1 and 0, this means that theta will be in the fourth quadrant. In the fourth quadrant, cotangent theta is also negative. Yes, because sine is negative and cosine is positive in the first quadrant. So it means cotangent is negative. So it means that when I want to remove that absolute value sign, I also have to put a minus sign there. So you see that, and then this minus sign and that minus sign are cancelled. So it doesn't matter. If x is between 0 and 1, I have this. If x is between minus 1 and 0, I will have this. But again, because these minus signs are cancelled, I eventually get that one. So if you don't mind, let me clean this. For that reason, I can only use this one. But you have to analyze the situation. Okay. Now I think everything now is in order. I just put everything back because what I needed is just cosecant and cotangent in both cases. So what I will do, I would write that I is equal to minus a half. Instead of cosecant of theta, I can put 1 over x. And then multiplied by cotangent theta, so that 1 over x goes to the denominator. So it becomes square root of 1 minus x squared over 2x squared. And then what I have plus 1/2 ln of absolute value of cosecant theta, which is 1 over x, plus cotangent of theta, which is the square root of 1 minus x squared over x, and then plus a constant c. Okay, now this is actually correct, but in order to get the same answer which is provided by the problem, if you don't mind, let me take the common denominator and write that term first. So this becomes ln of absolute value. Here, this becomes x, the common denominator, and then this will be my numerator. And then I would write this for you, 1 minus x squared over 2x squared, and then plus a constant c. But then, of course, I can continue a little bit more. So I can write it as ln of the numerator, which is ln of the absolute value of the numerator. But the numerator is non-negative, so I don't need to emphasize on that. So I can remove the absolute value sign and replace it by a pair of brackets, minus ln of the denominator. The denominator is absolute value of x because I have the possibility for x to be negative, so I have to keep the absolute value sign here. And then, of course, I can write this here. And that is exactly the answer that we are supposed to get for this integral. Okay. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.